Right, so we're going to look at significance testing with the normal distribution. Now, it comes from, what we look at first is the distribution of sample means. And this, if you remember the experiment, Miss Hoyle's experiment that we did with the Smarties, where we saw that when we took something that was normally distributed with mean, mu, and standard deviation, sigma, when we looked at the sample means from that distribution, they had the same mean, but their spread was less. They were more concentrated. And so we say that if our original distribution is normal with mean mu and standard deviation sigma, then the distribution of the sample means, if n is the size of your sample, is mean mu, but standard deviation sigma over root n, and of course we write that in our normal distribution, we have sigma squared over n. Right, so a question that you could be asked about the mean about sample means before we start significance testing. So the lifetime of a light bulb is X hours, is modelled in the normal distribution. Sorry, I've instantly put X bar. So the model X hours is modelled by normal distribution, where your mean is 10,000 and you've got an unknown variance standard deviation. 5% of samples of 100 light bulbs. So instantly you can see that n is 100, have a mean lifetime of less than 9,000 hours. So you know that if that's our distribution of x, our distribution of x bar will be normally distributed with exactly the same mean, but you've got a sample of 100. So that's going to have a variance of sigma squared over 100. You've been told that the probability of being less than 9,000, so less than 9,900. Now, because this is the normal distribution, we don't ever have equal to, because we can't find precisely equal to. We've been told that that's 5%. Now, when I don't know the mean or the standard deviation, I have to use my standard normal distribution, which is Z. And Z is normally distributed with mean 0 and standard deviation 1. And I'm looking at a less than, so if I visualise that normal distribution, I know that I want it to be less than 5%. So you can see that the value of Z you're going to want to find is going to be negative. So what you're going to do is you're going to use your inverse normal. So you are looking at your left tail, you've got a probability or an area of 5%. Your standard deviation is 1 and sigma, and mu, your mean is 0. So if you put that into your inverse normal, you'll get Z is minus 1.64. You know that Z is X bar minus mu over the value you have for your variance. So you're now going to substitute those in. So you're going to get minus 1.64 equals 9,900 minus your mean, which is 10,000, all over sigma over root 100, which of course is 10. And all you're going to do is rearrange that algebraically. If you rearrange that algebraically, you don't need me really to do that for you. You are going to get sigma is roughly 609.8. Okay, hypothesis tests for a mean. Okay, this is more straightforward than binomial significance testing. The reason for that is because it's a continuous distribution and your values are exact. You don't have to worry about getting correct whole integer values. And because of your exact values, then this statement here is simpler than it was in the binomial. The probability of incorrectly rejecting the null hypothesis is the level of significance. So if you're testing a 5% level of significance, the probability of incorrectly rejecting that null hypothesis will be 5%. Okay, so again, I've put that more in a straightforward statement there. In the binomial, it could equal the significance level or be less than. So what I'm going to do is I'm going to do each question using test statistic, which we tend to think is the easiest, and then we're going to do each one looking at the critical regions. If you are asked or told to use the critical region method, you must use the critical region method. If you are not, you can choose whichever one you like to do. Right, it is believed that the healthy level of testosterone in blood is normally distributed with mean 24 and standard deviation 6. Following a race, a sprinter gives 2 samples with an average of 34, whatever that is, N-mole, whatever, biologists. By the way, 2 samples, sample size of 2 is fairly rubbish. So this question does not bode well. Is this sufficiently high? So they are saying at the 1% level of significance to suggest that the sprinter's testosterone level is above the mean. So first of all, you'll be asked to construct a null hypothesis, and you can see that you are looking at a mean of 24, population mean of 24. Looking further into the question, you can see that they are testing to see whether this is going to be above the mean. So your alternative, actually I'll put that underneath because that's what we tend to do. Your alternative is greater than 24. You're now going to look at how the sample means are distributed. So your sample means are normally distributed with mean, mu, and your variance, which of course is your standard deviation squared, so 6 squared, which is 36, divided by your rather small sample size. So that's how things are distributed. So what we're going to do is we're going to find the probability of seeing greater than 34. There's your mean, 24. I like to visualise 34, that's greater than, so we're looking at finding that probability there, and from your sketch you can see that that's going to be less than a half. You get your calculator, you are in your menu for stat, you are just doing normal, you're doing normal CD, so your lower limit is 34, your upper limit is an enormous number. Your sigma is the square root of 18 and your mu is 24. So you would substitute that into your calculator and you find the probability of x bar being greater than 34 is 0.009. Now compare this with your level of significance, and your level of significance was 1%. 0.009 is less than 0.001. So the probability of, under the null hypothesis, of seeing what you've seen, those testosterone levels, is highly unlikely. Therefore, there is sufficient evidence to reject the null. There is sufficient evidence to reject the null. You'll get 1 mark for saying that. And then you must put it in context. So if you go back to the question and make sure you put it in context, look at the wording of the question, then there is sufficient evidence to suggest that the sprinter's testosterone level is above the mean. So we would say at the 5% level, I'm so sorry, it's the 1% level. at the 1% level, there is sufficient evidence to suggest that the sprinters' testosterone levels, so testosterone levels are above the mean. So you must say what you're doing with the null, and then you must put it in context. Right, if you are going to do this with critical regions, you would have exactly the same null and alternative hypothesis. You have exactly the same distribution. So what you're doing here, because your null hypothesis, if you go back and have a quick look, you've got mu is 24 as your null, and your alternative is mu is greater than 24. Because, so if we just quickly write those down so you know what you're dealing with, your alternative is mu is greater than 24. So what you're going to do is you're going to have visualise your critical region. So there's your mean. Here's your critical region. And if you look at your level there, you are looking at 1%. You are looking at 1%. So what you would then do is you would get your calculator, you would go into your inverse normal. So get your calculator, you go into stat, your distribution, normal, you would go into stat, your tail is right. Just move that up a little bit so you can see it. Your tail is right. Your area is 0.01. So your tail is right, your area is 0.01. Your mu, your sigma is root 18, and your mu is going to be 24. So you've got your sigma is root 18 and your mu is 24. And so I've got in my answers here, my critical region, x bar is greater than or equal to 33.9. So you can then see that 34 is in that rejection region. 33.9, 34 is greater than 33.9, and therefore you would have your same level, you'd have your same conclusion. Make sure you give the full details of conclusion, but it's reasonably close. Right, next question. So the school canteen sells coffee in cups containing 250 millilitres. It's known that the amount of coffee in a cup is normally distributed with standard deviation 6 millilitres. Adam believes on average that the cups contain less coffee than claimed. He wishes to test his belief at the 5% significance level. He measures the amount of coffee in 10 randomly chosen cups. Okay, so let's set the scene. First of all, the null hypothesis. You are looking at mu being 250 millilitres. The alternative hypothesis. You are looking at mu being less than 250. So you've got a less than there. Right, let's look at how the sample means are distributed normally. So your mean is 250 and you've got a standard deviation of 6. So you're going to have 6 squared over your sample size, which is 10. So there's our normal distribution of sample means. If you visualise what that's going to look like, there's your 250. You've been asked to find the probability, so we're looking at a less than. So what we're going to do is find the probability of x bar being less than 248. normally it's going to be less than a half. So you go into your normal distribution, your NCD, your lower limit is obviously something very small, your upper limit is 248, your sigma is going to be the square root of 3.6 and your mu is 250. If you put that into your calculator, the probability of x bar being greater than 248 is 0.146. 0.146 is greater than 0.05. So, the probability of seeing this under the null is reasonably big. It's definitely bigger than 5%. Therefore, for 1 mark, there is insufficient evidence or not enough evidence to reject the null at the 5% level. And then for your second mark, you will put it into context. So putting this into context, you will then be able to say that there is not enough evidence to say that the cups on average contain less coffee at the 5% level. To do this with a critical region, what you would do is you would have you've got exactly the same setup, you've got the same null, you've got the same alternative, so obviously your null again was 250 and your alternative was less than 250. So you are looking at a critical region, so there's your mean, you are looking at something to be less than that, and that's an area of 5%. So to set up your critical region, you go inverse normal, and you're going to put these in. Your tail is to the left, your area is 5%, your sigma, so these bits are the same as what we've just done, square root of 3.6, and mu is 250. And what you're then going to get out of there is 246.9. So your critical region is x bar being less than 246.9. That's what that is there. So any value that's less than 246.9 will be rejected. Now, 248 is greater than 246.9. So you do not have sufficient evidence to reject this at the null. You do not have sufficient evidence to reject this at the 5% level. And then again, you will put that in context with the amount of the question referral to coffee. Right, and our last type. So this type would be what we would call a two-tailed test, and we'll see this when we set up our hypotheses. The wingspan of a species of butterfly is known to be normally distributed with mean 10, standard deviation 1. A scientist thinks she may have found butterflies that belong to a different species with a different wingspan. The mean of a sample of 6 of these butterflies is 11.2. Test at the 5% level of significance, okay? So the key here is different, all right? So we are looking at a change. It's not greater than or less than. So our null hypothesis, remember, we're looking at mu is 10, and our alternative hypothesis, we are looking at mu being not equal to 10. We know that x bar is normally distributed under the null with mean 10, and our variance, obviously 1 squared over the sample size of 6. So we've got variance 1 over 6. So, but we know that this is two-tailed, and because it's two-tailed, you are going to have to halve that level of significance. It's 2.5%. So visualize what we're looking at. Your normal distribution, symmetrical about the mean. So we know that 2.5, we're looking here, so you've got We are testing 11.2. So we know we are looking to find the probability of seeing 11.2. So 11.2, we are definitely looking at this side. We've halved our level of significance, haven't we? So we've halved that. So what we want to do is find the probability of being greater than 11.2, and we will then compare that with 2.5%. So our lower is 11.2, our upper really big. We know that sigma is going to be the square root of 1 over 6, or 1 over the square root of 6, and we know that mu is 10. So the probability of being greater than 11.2, if I put that into my calculator, it's going to give me 0.0016. Now 0.0016 is less than 2.5%. So the probability of seeing this happening is highly unlikely under this model. It's certainly less than 2.5%. So we have sufficient evidence to reject the null hypothesis. Therefore, we would then put it back in context. There is sufficient evidence to say that the 5% level, this species of butterfly, is different. And then again, we could have done this using critical regions if we preferred, or we might have been asked to. Again, you've got the same hypotheses. You've got your null, where the mean is 10, and you've got your alternative, where the mean is not 10. So you are looking at finding two critical regions. You halve them, so each one is 0.025. So what I've done when I've put these into my inverse normal, I look at a central tail. My area, so obviously it's 1 take away 5%, so 0.95. Sigma is the square root of 1 over 6 as before, and mu is 10. And what happens is, if I then put them into my calculator, my critical regions are x bar greater than 10.8 or x bar less than 9.2. So I will reject if they lie in either of those regions. I know that 11.2, so if I'm thinking that that's 10.8, that's a rejection region, and that's 9.2, about my mean of 10. You can see 11.2 does lie in that region. 11.2 is greater than 10.8. Therefore, at the 5% level, you have sufficient evidence to reject the null, and then again, go back and put it in context. You have significant evidence to show that, to say that it could be a different species of butterfly. Remember, with the mean, important thing, with the mean, you are looking at sample means when you do our significance testing. With the binomial, you are looking at proportions and probability.